Well, thank you. As Dr. T mentioned earlier, one of the grand challenges is looking at our urban infrastructure. And if you read The Economist last month, they noted how there's so much technology in vehicles today, yet they're not seeing that in structural systems. So we don't have the monitoring going on. So I'd like to talk about that, the innovation associated with structural health monitoring. In Texas, we probably are somewhat of an innovator in that we have 60,000 bridges in the state, and 2 of them are monitored on a continuing basis. That percentage might seem quite low, but it's actually higher than almost every other state in the country. So we believe that there is quite a need for this sort of innovation. I'm actually working on a team of structural, mechanical, and electrical engineers at UT with National Instruments to try to develop the systems that could be used for this purpose. Our goal is to come up with lower cost systems, and much like we heard about the personalized cancer detection yesterday, coming up with systems that can be adapted for the individual structures that we're trying to monitor. If you look at some of the structural health monitoring systems that have been used in the past 10 years, they fall short because they're not sensitive enough to pick up the most important things for each individual structure. So in terms of societal impact, we need only think about the I-35W bridge in Minneapolis. Everyone saw this within about 30 minutes of it happening during the rush hour in 2007. And the idea is that if these structures were monitored, there may be a chance to prevent this sort of catastrophic collapse. Now, we don't hear very often about bridge collapses, but in a recent study in the US, taking a 12-year period ending in the year 2000, there actually were 500 bridges that collapsed. So out of 600,000 bridges in the entire US, 500 collapses in a 12-year period. It's not a large number, but it certainly is greater than 0. And it's the risk that we would like to see reduced. In terms of the opportunities, I'm looking primarily at highway bridges, but if you think about any other type of urban or civil infrastructure, there are older systems out there. We all heard about the gas line explosion in California this summer. So it's the same type of thing. The system had been in service for a long time, and there was deterioration. So if you look at this plot, about 10% of the bridges in the country are classified as structurally obsolete. That means that we don't have the financial resources to replace all of these structures, but we have the opportunity to enhance our understanding of them. So let me give you an example of the bridge that we are currently using as our test bed. This bridge was constructed in 1935. It is about 10 miles south of San Antonio, and it is the northbound I-35 over the Medina River. So it's carrying approximately 4,000 vehicles a day. When you look at the primary longitudinal girders in this bridge, they're actually made, they're built up sections. They're steel sections. They're made from steel plate and angles that are riveted together. This is clearly not a system that we would choose if we were building a bridge today, but it's in service, and it's been in service for quite a long time. Because there are only 2 girders in this bridge, it's classified as being fracture critical, which means that every 2 years, the inspectors from TxDOT need to do a detailed inspection. They basically do an up-close, hands-on inspection to look at what has happened to the bridge in that 2-year period. And if I give you a detail of one of these connections, you can see that there's a cracking of that top flange. The angle that's used for the top flange is 8 inches. You also, well, you can see a couple marks there. Thank you. I'm probably not going to find this. Well, oh, thanks. Okay, there we go. You can see here is where the crack, so this is the crack. You can see the crack was at this point when it was inspected in the year 2000, and basically the most recent in this picture is from the year 2007. So my guess is that this crack is growing at a rate of about 1.5 inches over 7 years. This is not something that's moving quickly. It's not something where we need to be measuring real-time response at 100 hertz continuously, but we'd like to know if this crack is growing and if the stress distribution in the bridge were to change with time. And that's the type of thing where we're trying to come up with monitoring systems that can be used for this specific bridge and the applications that we're interested in. The traditional type of structural health monitoring system would be to use a kind of a global measuring device, use accelerometers and extract the natural frequencies of the bridge. Well, I can guarantee you that a change in crack growth of 1.5 inches over 7 years, you're not going to be able to pick that up from the natural frequencies of the system. And actually, the change in the natural frequencies just due to the thermal cycles are going to be many orders of magnitude larger. So the potential for innovation is coming up with what we can do, how we can monitor, develop the monitoring systems for specific bridges. In terms of the barriers, the cost is probably the primary barrier. If you've read any of the papers recently, you know that TxDOT is being hammered. Their budget will likely be is being scrutinized, and the cost of these monitoring systems is often prohibitive. When you hear the numbers, they'll tell you that, oh, the cost of installation of a real-time monitoring system, it might be 0.5% of the total cost of the bridge. And that doesn't really seem like much. But if you are the person responsible for this bridge and you're faced with $1 million investment to install a monitoring system, and then something like $100,000 each year to monitor the data, that is a huge investment. And that's the same maintenance budget that you're using to do all the other repairs in the district. So actually, the cost is quite important. Secondly is the interpretation of the data. There was a recent study that looked at the Korean experience, where they've actually done a number of monitoring systems on highway bridges. And they found that after a 10-year period, they really weren't getting that much out of the data. And they had so much data they couldn't keep up with interpreting it. And I think it's because they didn't have the specific systems for each bridge, or they didn't have the flexibility to design the specific systems for each bridge. They were using this global monitoring, and it wasn't sensitive enough. It's much like trying to use the full-body scanners at the airport as some sort of cancer screening. It just isn't going to work. And so the decision in Korea was, well, we've had 10 years worth of information, and it hasn't given us what we need. We're going to just take them out. We're not going to continue monitoring. So I think there's a great amount in terms of the design of the system and coming up with simple ways to interpret the data. Finally, and this probably might be the most difficult thing, is that the states are bound by federal regulations to inspect the bridges on a 2-year period. They cannot say, well, I'm going to install a monitoring system, therefore I can cut back on my inspection costs. You saw that it was a fairly small team of people looking at that bridge in San Antonio, but they're also blocking a lane of traffic to do it. The costs tend to build up. So because of these federal regulations, it doesn't matter if my bridge was built 75 years ago or built 5 years ago. I have to have the same type of inspection. And so if we can relax some of these requirements and allow real data to be used to determine the most vulnerable bridges, I think that's where the greatest potential lies, but it's really a political decision, and that's where it might be the hardest to do. So thank you very much.